Today we will be exploring the fundamental principles of adsorption isotherms, which allow us to quantify how gases and solids interact with solid surface. To begin, we define the adsorption isotherm as the mathematical relationship that characterizes the amount of adsorbate on a surface as a function of its either partial pressure for gases or concentrations for liquid at a fixed temperature. In a closed system, you will notice the gas pressure initially decreases and then stabilizes, indicating that a stable state, which is the equilibrium state, has been reached. At this point, the rate of molecules attaching to the surface or adsorption is exactly equal to the rate of the molecule leaving the surface, or known as desorption. We can quantify this state using the fractional coverage, denoted by the Greek letter theta. This value represents the ratios of the number of occupied sites to the total number of available sites. The variations of theta with pressure at constant temperature is what we specifically refer to adsorption isotherm. This figure illustrates the variations of the pressure in the system with the number of adsorbent adsorbed on the adsorbate. Initially, there is no molecules introduced into this vessel, so the pressure of the system is 0 and number of molecules adsorbed on this surface is also 0. Next, if we introduce 4 molecules and 3 of them are adsorbed on the surface, therefore the number of molecules adsorbed is 3, while the pressure of the system will become 1. Following that, another 4 molecules were further introduced, and only 2 of these gas molecules are suspended in the gas phase. So there are 6 molecules adsorbed on the surface. Therefore, the number of molecules adsorbed is 6, while the pressure of this system is 2. Another 8 molecules were further added, and upon this total 16 molecules, 9 molecules were adsorbed on the substrate. So the number of molecules adsorbed become 9, while the pressure of the system now is 7. If we further increase the number of molecules in this system to 24 molecules as a total, and we will see that the pressure of the system increases, while the number of molecules adsorbed remain not much changes compared to when they have only 16 molecules. So we see that as we introduce more molecules into the chamber, the pressure increases and subsequently more molecules are forced onto the adsorbent surface until it achieves the equilibrium, where when you further added the molecules, there is no changes in the number of molecules adsorbed. We can plot this experimental data as the fraction of molecules adsorbed, theta, versus pressure. The formula theta equals to n over n maximum, which is the number of adsorbed molecule to the maximum available site, will help us to visualize how close the surface is being completely covered. Another common way to express the extent of adsorption theta is the ratio of x over m, where x is the mass of the gas adsorbed and m is the mass of the adsorbent. As pressure increases, we eventually reach a saturation pressure, Ps, beyond which no more gas can be adsorbed at that temperature. The first mathematical relation for these isotherms was proposed by Freundlich in 1909. This is an empirical model used for multilayer adsorption on the heterogeneous site, which means that the surface sites are not all identical in the energy. And this model is not valid over a very large range of the adsorption data. Relationship between the quantity of gas adsorbed on the surface of the adsorbent at different pressure is expressed using the Freundlich equations, where we have the K and N are the constant with N greater than 1. This equation, X is the mass of the gas, M is the mass of the adsorbent, and P is the equilibrium pressure. The constant K and N depend on the nature of the solids, gases, and the specific temperature. Low pressure, the graph is nearly a straight line. The value of N is equals to 1, showing that the amount of gas adsorbed is directly proportional to the pressure. At high pressure, the isotherm levels off, and adsorption becomes independent of pressure. The value of N is equals to 0. Further increase of pressure did not change the amount of the gas adsorbed. While at the intermediate pressure, the value of N lies between 0 and 1, and the relationship follows the fractional power of pressure. The peak of this curve is the saturation state, which occurs when the adsorbate forms a uniform molecular layer on the surface. Even if the pressure is increased beyond Ps, the extent of adsorption remains the same, where there is no changes on the amount of gas adsorbed. Temperature plays the crucial role. As the temperature increases from 195 Kelvin to 273 Kelvin, we can see that the extent of the adsorption decreases. To verify the Freundlich model, we take logarithm on both sides to get a linear equation. Therefore, we have a log x over m equals to log k plus 1 over n log p. A plot of log x over m versus log p should yield a straight line, though it may show slight curvature at extreme pressure. But we can say that the data that we obtain from the experiment can be fitted into the Freundlich model. As mentioned earlier, adsorption isn't limited to gases. Porous adsorbents can also remove dissolved solutes from solution. A classic example is using activated charcoal to remove color impurities from a solutions, like in a litmus solutions. There, add in some charcoal and the color of the litmus was being removed by using the charcoal. Factors that affect adsorption of solution. There are four main factors affect the adsorption of solution, which are the surface area of the adsorbent, the temperature of the solution, the adsorbate concentration in the solution, and lastly, the nature of the adsorbate and also the adsorbent. The temperature of the solution. Just like with the gases, an increase in temperature leads to a decrease in the extent of adsorption in solution. So when the temperature was increased from here to this increasing in the temperature, the amount of the adsorbate adsorbed on the charcoal become less. This area of the adsorbent. Increasing the surface area from this size to this size of the adsorbent will increase the extent of adsorptions. So you will see that there are more blue dots adhere or adsorb on the surface of this charcoal compared to the smaller surface area charcoal. Charcoal with its tiny pores or with the porosity which is higher will provide a massive surface area, making it more preferable for the process of adsorptions. So the porous material will have a higher adsorptions compared to the non-porous material. Regarding concentration, as the concentration of the solute increases, the extent of adsorption also increases. The nature of the chemical bonding between the species involved determines how strongly they will adhere. So the nature of the adsorbate and adsorbent will determine how good will be the adsorption. We can adapt the Freundlich equation for solutions by replacing the pressure with equilibrium concentration C, giving us x over m equals to the constant multiplied the concentrations to the power of 1 over n, where C is the equilibrium concentrations when the adsorption complete in solution. If the logarithmic plot of log x over m versus log C is a straight line, the Freundlich isotope is valid for that solution. The Freundlich adsorption isotope can be tested experimentally by adding equal masses of charcoal to different concentrations of acetic acid, and then let the mixture to stir for some time. So that filter off the charcoal and collect the filtrate to determine the final concentrations of acetic through titrations. If the logarithmic plot of log x over m versus log C is a straight line, the Freundlich isotope is valid for the solutions. And the result of the experiment also support the hypothesis where the extent of the adsorption increases with increase in the concentrations of the solute. There are limitations to the Freundlich model because it lacks a theoretical background, and it is mostly applicable at low pressure. Besides, the constants are also varied with temperature. This Freundlich equations or the model remains highly useful for determining adsorption extents at low pressure for both gases and solutions. Langmuir adsorption isotherm. Failure of Freundlich adsorption isotherm at higher pressure indicates that his concept is not entirely correct. In 1916, Erwin Langmuir introduced a more theoretical concept based on kinetic molecular theory of gases. He proposed that at equilibrium, the surface rates of adsorption and desorption are equal, with zero net accumulations. The Langmuir model relies on three key assumptions. Number one, adsorption cannot exceed monolayer coverage. They can only form a monolayer on the substrate. All sites are equivalent and homogeneous. All the surface has the same properties. They are homogeneous. And there are no lateral interactions between the adsorbed molecules. Those molecules that are adsorbed on the substrate cannot have interactions with their neighboring adsorbate. According to Langmuir, the gas molecules strike the surface of a solid. Some of the striking molecules get adsorbed and others start to evaporate or dissolve. Therefore, a dynamic equilibrium is established between the number of adsorbed and also the dissolved molecules. In his derivation, Langmuir viewed adsorptions as dynamic equilibrium. So, if theta is the fraction of the surface covered, then 1 minus theta represents the fraction of the vacant area. The dynamic equilibrium can be written as adsorbate A plus the absorbent M and form the adsorbate on this adsorbent AM, with the rate constant Ka for adsorption and Kd for desorption. At time t equals to 0, the pressure is equals to the initial pressure Pi, and N represent the total number of sites available. And at the time t, there is no adsorbate adsorb on the adsorbent, so it is equals to 0. At time equals to equilibrium, the pressure of the system now become P, where it is the partial pressure for A. And the number of sites available is equals to N multiply 1 minus theta. Theta is the occupied fraction. So 1 minus theta is this area, which is unoccupied fraction. Multiply the total number of sites available. And after it achieves equilibrium, then there will have some adsorbate adsorb on the adsorbent. So it is equals to theta, the occupied fraction, which is the surface coverage by the gas molecule. The rate change of surface coverage, theta, due to the process of adsorption is proportional to the partial pressure of A, which is identified as P, and also the number of vacant sites available, which is the total number of vacant sites multiply the fraction of the unoccupied site, that is 1 minus theta. Theta is the surface coverage by the gas molecule, and it can be quantified from the ratio of the number of adsorption sites occupied to the number of adsorption sites available. That we can derive the rate of adsorptions d theta dt, which is equals to the rate constant of the adsorption Ka multiply the pressure of the system multiply the total available sites for the adsorptions. And the rate change of theta due to desorptions is proportional to the number of adsorbed species and theta. So if they have a lot of the species that has already been adsorbed on the substrate, then it will speed up the rate of the desorptions. And the equations for the rate of desorptions equals to negative d theta dt, which is the reverse process for the adsorptions, equals to the rate constant for the desorption multiply the number of adsorbed species and theta. At equilibrium, the rate of adsorption equals to the rate of desorption. So there is no net change, and solving for theta, it will give the Langmuir isotherm. So you have the Ka multiply pressure multiply N multiply 1 minus theta, which is the fractions that is unoccupied, equals to the desorption rate. And we rearrange it, we get the function for the theta equals to equilibrium constant K multiply the pressure of the system divided by 1 plus K equilibrium constant multiply the pressure of the system. And the equilibrium constant is equals to the rate constant of adsorption divided by the rate constant of desorption. This slide shows the step-by-step work to derive the Langmuir isotherm equations when we equate the rate of the adsorptions, which is equals to the rate of desorptions, meaning that when the process is achieved equilibrium. So we move the Kd, the rate constant for the desorptions, to the other side, then we get the piece of the expressions here, Ka over Kd, multiply the P, which is the pressure, partial pressure of the system, multiply 1 minus theta, which is the fractions of the unoccupied sites, equals to the theta, the fractions of the occupied site. And we know that Ka over Kd is equals to the equilibrium constant K, capital letter. So we replace it with the equilibrium constant, and then we move the 1 minus theta to the other side, which we will get these expressions here. After that, we inverse the whole expressions here to become 1 over. And then we rearrange these equations, and it turns out to become something like this. After that, we move the -1 to the other side. Okay, then we will get 1 over theta equals to 1 plus K multiply pressure over K multiply pressure. And we inverse it. We will get theta equals to equilibrium constant multiply the pressure over 1 plus equilibrium constant multiply the pressure. So this is the Langmuir isotherms equation. If we look into these equations and we discuss the effect of the pressure on the fractions of adsorptions into 3 regions with low pressure, high pressure, and at the intermediate pressure. At low pressure, the p-value is very small. Therefore, the theta will be proportional to the equilibrium constant multiply pressure, which is theta equals to Kp. Therefore, we say that at low pressure, the amount of the gas adsorbed will be proportional to the increase of pressure. While at a very high value of pressure, then theta is equals to 1 because Kp over Kp is equals to 1. So at very high pressure, the amount of the gas adsorbed on the adsorbents is not depends on the pressure, meaning that when you further increase the pressure, it will not change the fractions of the adsorb. While at the intermediate pressure, the amount of the gases adsorbed on the adsorbent is increasing as the pressure increase. Well, the n is range from 0 to 1 at this intermediate region with the pressure. Now let's look into the example which involved the adsorptions of carbon monoxide on charcoal at 273 Kelvin. You are asked to find the equilibrium constant K and the volume corresponding to the complete coverage. These are the data given at different pressure and also the volume for carbon monoxide. We use the Langmuir isotherm to determine the respective equilibrium constant and also the volume required for the monolayer coverage on the charcoal. So we relate the theta, which is the surface coverage, with the volume of the carbon monoxide, where theta equals to V over V infinity. And the V infinity here is referring to the volume corresponding to a complete coverage, meaning that the volume that is required for the carbon monoxide to form a monolayer on the surface of the adsorbent, which is the charcoal. So we can rearrange the Langmuir isotherm equation to obtain this that is related to the volume. In the isotherm equations, it doesn't have the volume, so we have to replace the theta with V over V infinity, which is the volume available for the carbon monoxide to the volume of the carbon monoxide that form a monolayer on the charcoal. So we can rearrange these equations and transform the theta with the parameter of volume. By having these equations here, then we can plot a graph of pressure divided by the volume against pressure. So we will get a straight line with a slope that is 1 over V infinity, and the intercept, we can obtain the value of the equilibrium constant. In this slide, it shows you how to obtain the equations, which will enable us to plot a linear line from the Langmuir isotherm. So first of all, we get the Langmuir isotherm, and then we rearrange it to obtain these expressions. After that, we divide both sides, left and right, with the equilibrium constant. Okay, so next is we get this one. And at the same time, we also need to replace the theta with V over V infinity. So we have this, which is representing the theta. Okay, similar to this one. And next is that we divide both of the sides with V. So after we divide V, then we will get the final equations, which is a linear equations. And with the data given, we have to divide the pressure with the volume so that it will give us the value for the y-axis. And then we also have the value for the pressure. Therefore, we can plot P over V versus P for the linear line in order to get what is the value for V infinity and also the equilibrium constant K. So the least square slope is about 0.009. Therefore, the volume that is required for the carbon monoxide to form a single layer on the adsorbent, which is the charcoal, is 111 centimeter cube. So by having this value, we can further to find out what is the respective value for the equilibrium constant. Equilibrium constant is equals to the value for the intercept, and the intercept is 1.2. So we can find out what is the value for equilibrium constant. So that is one of the example. It shows that how to determine the respective volume to form a single monolayer, and also the equilibrium constant for the process of adsorptions. From the beginning until this slide, we only concern about the adsorptions of the molecule, which is just attached to the surface of the substrate through the van der Waals forces. And sometimes a molecule like A2, it will dissociate upon the process of adsorptions, and it will occupy two sites instead of one. So this is one of the example where it involves the adsorptions with dissociation. So similarly, at time t equals to 0, the pressure of A2 is Pi, and n is the number of the sites that is available. So in this case here, we have a 2n, and the sites that is occupied, which already form the adsorbed molecule on it. Then at the initial time, t is equals to 0, it is 0. While the process of adsorptions proceeds, then it will achieve equilibrium. The process of adsorptions and desorptions occur simultaneously, and the rate are the same. So at time equals to equilibrium, the pressure is equals to pressure for the system, while the space that is available for the process of adsorptions, or the available of the empty space, is equals to 2n multiply the fractions of the unoccupied site, which is 1 minus theta. Theta is the surface of the coverage, which is already occupied by the molecules. So, and then those that has been occupied is 2 times the site that is already occupied by the molecule, and theta. And this equilibrium, it shows the process of adsorptions, which involve the dissociations of A2 to become 2A. Now you know that for the process of adsorptions, it has two different types, but generally in the Langmuir model, a molecule just needs one open spot for the process of adsorptions. If the molecule dissociates upon the process of adsorptions, then they will require two sites to land on the surface of the adsorbent. And the rate of adsorptions is given by these equations here, where it involves the pressure. Just like a non-dissociative adsorptions, the rate of adsorptions is proportional to the partial pressure of this adsorbate, because that determines how frequent the molecules strike the surface. In addition to that, in the rate law here, we also has the square term, which is n multiply 1 minus theta. And this is the most important change, since the molecule just find two sites that simultaneously allow the molecule to adsorb on the surface. So the probability of this happening is proportional to the square of the number of vacant sites, which is n multiply 1 minus theta. N is the number of vacant sites, 1 minus theta is the fractions of the unoccupied site. So this n multiply 1 minus theta represents the available sites where the molecule needs two pieces to align perfectly on the surface of the adsorbent. While in addition to the process of adsorptions, the process of desorptions will also occur. When they achieve equilibrium, both of these rates are the same, so they are equal. The process of leaving the surface also becomes more complex when it involves the process of dissociations for the molecule upon adsorptions. For a molecule to dissolve, two separate atoms adsorb on the surface must find each other and then they recombine. After that, they leave as a molecule with two atoms, which is A2. So these equations express the rate of desorptions. This is a second order kinetics because the desorptions require the encounter of two atoms on the surface to recombine. So the rate is second order in the number of atoms present and theta. The frequency of encounter is also playing the role here. The rate depends on how often these two atoms bump into each other while vibrating or motions on the surface. So the more atoms you have, which is if you have higher value of theta here, then much more likely they are able to find a partner and dissolve from the surface, which is why we square the occupied site term here. So that is the equations for the rate of adsorptions and rate of desorption. At equilibrium, the rate of adsorption equal to the rate of desorption. So with that, we equal both of the expressions, and at the end it comes up with the theta equals to the expressions here, which is a modified Langmuir isotherm. Well, this slide it shows the step-by-step how to obtain the value of the theta from the beginning, where you have the rate law for the rate of adsorptions and also the rate of desorptions when they achieve equilibrium. So from there, we replace the Ka and over Kd with the equilibrium constant. For the process of adsorptions involve the dissociations of the molecule. So we get this term here, and from this term we square both sides, which reach this step. After that, we simplify this part here, where you have the square root and also the square, so it will become theta over 1 minus theta. And then we transfer the 1 minus theta to the other side. So we get this one, okay, and multiply with the square root of Kp. And the next step is to move the minus square root Kp multiply theta to the other side. Then you have square root Kp equals to theta plus square root Kp multiply the theta, and factor the theta from the expressions here. So after we factor the theta, then we move the 1 plus square root Kp to the other side, which we will get this modified Langmuir equations for the adsorptions with dissociations. If we compare the Langmuir isotherm for the system with dissociation and without dissociation, then we will realize that the effect of pressure on the system is playing a weakly role in the system for the process of adsorption with dissociation. This slide it shows the differences between the standard, which is without dissociations of the molecule upon the adsorptions, and also the dissociative adsorptions. In this graph here, it shows the non-dissociative adsorption, and this follow the standard Langmuir equations. You will notice that at low pressure, the fractional coverage theta it increases quite sharply because it is proportional to the pressure. But for the dissociative adsorptions, where it follow the modified equation, the curve rise much more gradually at low pressure. This is because of the square root term, where the surface coverage for the dissociative adsorption depends more weakly on the pressure than it is if it is non-dissociative counterpart. And both of these graphs shows a family of curve corresponding to the value of K, which is labeled at the 0, 1, and 0.1. At high equilibrium constant with K equals to 10, these curves are the steepest for both of these cases. A high K value will indicate a strong affinity between the adsorbate and the surface, so meaning the monolayer fills up at a relatively low pressure. While at low K, where K equals to 0.1, the curves are much flatter for both of these cases. This indicates a weak adsorption, requiring significantly higher pressure to force the gas molecule onto the available surface sites. So what you can deduce from these curves here? If the curve rises quickly and follow a linear trend at the start, just like this one, so it is likely a non-dissociative adsorption case. If the curve is stretched out and rise more slowly due to the square root of the dependency, and it indicates that the molecules are dissociating into two atoms upon the process of adsorptions, with each atom that required their own sites to adsorb on the surface of this adsorbent. To conclude our discussion on Langmuir model, we must look at the thermodynamics of adsorption. Understanding the energy changes involved is just as important as knowing the surface coverage. First, let's recap the behavior of the fractional coverage theta. As we have seen in our previous discussion, theta increases as the pressure increases, meaning that the coverage of the surface will increase if you increase the pressure of the system, where you have more molecules of the gases are present. It only approaches a value of 1, which is representing a complete monolayer formations at very high pressure, when the gas is essentially forced onto a very single available site on the surface. A critical takeaway from our earlier slide is that the temperature significantly alters the extent of adsorption. Because of this, when you conduct experiment at different temperatures, you will obtain different curves and therefore different value for the equilibrium constant. We can leverage this temperature dependence to determine a key thermodynamic value, which is the enthalpy of adsorption, delta H, AdH. This represents the standard enthalpy of adsorption measured at a fixed surface coverage. To calculate this quantity, we treat the equilibrium constant K as a standard. We then apply the Van Hoff equation, which relates the changes in the natural log of K with respect to the temperature, delta T, to the enthalpy of the process, delta H. So by measuring how K change as we change the temperature, we can use this equation to find the energy released or absorbed during the adsorption process. This will provide us the information related to the strength of the bond between the adsorbate and the surface, and help us to understand whether we are dealing with weak physical forces or strong chemical interactions.